Okay, so as I said, I would do a damping factor on this particular amplifier, which had a fault on the output transformer. I like to connect the feedback winding to earth, as I said in my other videos. So now we're doing damping factors, so uh, we have to do that at the frequency, and we have to measure the output impedance, unloaded and loaded. So first of all, um, let's just look at the way I've connected it up. I'm measuring directly across the speaker output, and as you can see here, I've got two drills in there. I'm using them as a means of connecting the scope up directly into the amplifier without any wires. That's very important. Don't use wires. Get right in at the amplifier because that's crucial to the measurement. Anyway, that's what we're doing. We're going to measure the output on a scope of 1 kilohertz, as we can see here, set to 1 kilohertz, and the level I've got to adjust to 4 volts. Okay, so I'll just do that there. I think you might be able to see it's very, very awkward getting exactly 4 volts, and you must get it exactly to 4 volts. So there are 4 volts, 3 point, more or less 4 volts. I say more or less, contradiction. So I've got to actually get really, because of the way it all works, really got to measure 4 volts. Well, it keeps varying. There's a bit of noise on this scope. Yeah, I can see it's 4 volts now. 4 volts. So this is the theory. Impedance of the output equals the resistance of the load times the voltage unloaded over the voltage loaded minus 1. So that's it. Where Z out equals the output impedance of the amplifier, and V unloaded, VU, is the unloaded output volts, and VL is the loaded output volts, and RL is the load resistance. Okay, so it's quite simple. You measure the volts unloaded, you put the resistor across, measure the volts loaded, do the calculation, okay, and then you have to work out damping factor. So there's the formula with the figures put in, okay, and then when you get a value for Z out, you've got to put that value into the damping factor formula, which is simply the resistance of the load, which is 2.2 ohms, over Z out, which we just calculated there, and that will give us our damping factor at a particular frequency. So having done all that, connected that up, measured 4 volts there, unloaded, we take this out and put our load in, connect that into the amplifier, 2.2 ohms, and do the same measurement again and see how much this level drops. It will go from, well, 4 volts. Now you see why it'll only go down a little tiny bit. So you can see here on done previously, when I loaded it, the volts dropped to 3.88. They were 4. I put the 2.2 ohm load in, did the measurement again, measured the output on the scope, and it dropped to 3.88. And I did that at 1 kilohertz, and I also did it at 100 hertz. So I'll show you the figures, what happened. Formula, the calculations. So Z out equals 2.2 ohms, that's the load, times 4, which is the voltage measured unloaded without a resistor in the output speaker socket, and then with 2.2 ohm load into the speaker socket, connected into the speaker socket, it dropped to 3.88, and then the formula says minus 1. So we did that calculation, and you can see here I got a figure for the output impedance of 0.0682 ohms. Now you see why we're going to measure this directly at the speaker terminals and not using wire, because the wire resistance may have a detrimental effect on the measurements because of the wire resistance. So that's what we did, and then I worked the damping factor out as the resistance of the load, which is 2.2 ohms, divided by the Z out impedance, okay, there at 1 kilohertz, and the answer came to 29.32 at 1 kilohertz. Then I did the same thing again, changed the oscillator frequency to 100 hertz, did the same calculation, and as you can see here, the loaded voltage changed. It was, where are we, 3.88. At 100 hertz, it was 3.92. So the impedance changed at 100 hertz a little bit, and the voltage level increased. So there was slightly more loaded voltage at 100 hertz than there was at 1 kilohertz. That's the value of 1 kilohertz. So there we have it. Doing the calculation, made a mistake there, I had to cross it out. The damping factor came to 49. So at 1 kilohertz it was 29 or 29.32, and at 100 hertz it's 49, which is acceptable for this type of amplifier. When you come to transistor amplifiers, you can have damping factors in the hundreds, okay, but really that's an academic point, because the ability for this amplifier to stop the cone from flapping around too much at 100 hertz depends on how much resistance the amplifier presents to the speaker. Okay, so the more resistance across the speaker terminals, the less rather resistance you've got, the less the cone is liable to flap around and not be damped. So damping factor is the ability to stabilize the speaker cone at, particularly at low frequencies where the movement is the most. So that's what damping factor is all about. It's stabilizing the base to be tight and clean without the cone um, um, causing ringing. Ringing would be an oscillation of the cone as it goes in and out. If the damping is little, that means there's too much resistance across the speaker terminals at the output of the amplifier. There's not enough resistance. The resistance is not low enough to damp that ringing. So that's what damping is all about, and this is acceptable. A damping factor above 10 or 12 is acceptable, and it makes very little difference to listening, tests. People say it does, but I'm skeptical about that sort of thing. I think that damping factor is significant. It does have an effect, but on most amplifiers that you get, even old valve amplifiers like this one, damping factor above 20 is fine, and so that's what we've got here. We've got damping factor at 1 kilohertz, which isn't so important, of 29, and we have damping factor at 100 hertz, which is more important, of 49. So it looks as if this amplifier is okay. I haven't done the measurements with the damping control um, uh, altered at all. I backed it right off, so there's no, the damping control is set to 0, as it were. So there we are. I thought I'd just show you that. It's a very quick video. I'm going to run out of battery on my camera phone. in a minute. So that's the important formula. That's the easiest one to remember. Uh, Output impedance equals the resistance of the load multiplied by VU over VL, that's V unloaded, over V loaded minus 1. It's quite simple. And then damping factor is simply resistance of the load over that calculation there, Z out, that we just calculated. So thank you for listening. Thank you for viewing, and I'll catch you at some other time with some other repairs that I've done. They call me um, um, master of none, I think is the expression, isn't it? Um, when you an expert at all kinds of things, or so-called, you can repair all kinds of things, but you're a master of none, and that's me. I come into problems with all kinds of things, and I'd like to show you these on my other on my YouTube channel at some time or the other. So if you're interested in all kinds of repairs, from white goods to microwaves to toasters to amplifiers, you name it, I'll try and show you on this YouTube channel how to repair them or what goes wrong or how to test things. So thank you for viewing. I hope you found that interesting.